So you've been having some speakers live in person?
Yeah,
Okay.
we've had a couple who have been visiting or who are local to the area
Mhm.
come in, but we've also had a couple that have excuse me, a couple that have called in just like you are. So
Mhm.
we had Balaji from GFDL. Did you read Balaji's stuff? He had something on machine learning that Dan Lee might find interesting. I can send you a copy of.
Yeah, I think we talked about that last time we met, and I forgot to ask you about that again. So that'll be great.
Yeah, I'll send you that stuff. Okay. So we're live on YouTube, so let's have that conversation later.
Yeah.
Okay, nice. So I'll just wait one more minute, Ryan, and then I'll start.
Okay.
Okay, so I'm going to go ahead and start and introduce our speaker today. So it's my pleasure to introduce my friend and colleague, Ryan O'Loughlin, as today's speaker. Ryan will be presenting why we should want models to disagree, the value of error diagnosis and low skill models in climate science. So Ryan's research has revolved around a mutually beneficial relationship between philosophy and climate science. He focuses on philosophical analyses of the credibility and applications of climate models and model intercomparison projects, which he considers to be the powerhouse of climate change research. Ryan's interested in such questions as why and in what sense are climate models robust? Why do intercomparisons between different climate models tell us? And what is the value of disagreement in climate modeling? Ryan recently defended his dissertation titled The Role of Model Intercomparisons in the Department of History and Philosophy of Science and Medicine at Indiana University in Bloomington, where he worked with Elizabeth Lloyd. He is now assistant professor of philosophy at Queens College, part of the City University of New York institution. His notable papers on the topics that have been recently published include robustness reasoning and climate model comparisons, and model robustness in economics, the admissibility and evaluation of tractability assumptions. So thank you for joining us, Ryan, and I invite you to share your screen and begin your presentation.
All right. Thank you for that introduction, Monica, and thank you for inviting me to be here. So let me just to be clear, you're all looking at my main full slide presentation and not my notes, correct?
Yep, that looks great. Thank you.
Awesome. Okay. So why we should want models to disagree, the value of error diagnosis and low skill models in climate science. So first, maybe just a little background about me, although Monica's introduction is probably better and more informative than what I'm going to say about myself. I'm a philosopher of science, and I care about how knowledge is gained in climate science. So sometimes with a close study of how scientists use models, not only do we understand like the knowledge generation process better, but we can also maybe improve the knowledge generation process, make it itself better. And so this is one thing I hope to bring to you in today's talk. So I'll start with a philosophical debate about whether we can diagnose errors in complex modeling, and then move on to what scientists may learn from it, hopefully. So I know scientists sometimes like to read conclusions first, so I'll give mine here. So I propose that we could start building like an error repertoire for climate models. And now to be clear in this talk, I'm just focused on like the most complex models, general circulation models, or Earth systems models, if you prefer. But in this error repertoire, we can raise hypotheses about potential errors, design ways to test them, and collect the results. This seems like a straightforward or maybe simple idea, but at the same time, there are a lot of difficulties of implementing this. So, of course, scientists do diagnose model errors in practice, but the way that I've seen it, at least in the literature that I looked at, is more an isolated and scattered phenomenon rather than like a systematic thing. And so I'll explain why model error diagnosis in the multi-model context seems to be the way that it is, and why it maybe is challenging to do this systematically. And then a second message that I hope to bring is that low skill models also have their value in knowledge production. And I'll try to motivate this idea with a couple of case studies that I find interesting. So if you're still interested in what a philosopher has to say about how science works or how it should work, here's the agenda for today. So first, I'll start with a philosophical challenge that has brought me into looking at climate model error diagnosis. And although this is a philosophical debate, I did look also at the scientific literature, and I found evidence that some of this challenge has been partially taken on by scientists. But at the same time, I found evidence that scientists can and do diagnose errors in model intercomparison projects. So I'll present 4 cases of that. And then with these cases, I'd like to synthesize the strategies used by these scientists because, as I mentioned before, I believe these strategies can shed light on how we might build an error repertoire. And then, of course, I'll discuss the benefits of an error repertoire as well as the limitations of what building one would actually entail. And then lastly, I'd like to zoom into this idea of low skill models and show you how they are valuable in model intercomparisons, specifically in the context of testing weighting schemes and constraining some climate estimates. Okay, so first, what do philosophers argue about climate models? So there's this philosophical challenge called holism. The claim of holism is just that climate models are these holistic entities and we just can't evaluate their failures or successes in a piecemeal way. And so the reason behind this type of holistic claim is multifold. So first, oh, and by the way, the claim comes from a philosophy of science paper called Holism, Entrenchment, and the Future of Climate Model Pluralism, where they make a philosophical case for why we should believe in this holist challenge. And so the authors here, Leonard and Winsberg, they talk about 2 broad ideas. One is like the legacy of model code. So there are maybe instances of tweaking code to get a new submodel to work well with the rest of the model, and this may or may not be documented. Or just the difficulty of replacing old code with new code. And then the second part of the reasons for having this skeptical view is because of how climate simulations work. So the different submodels don't like run independently and then we compile all the results at the very end. Instead, the results come from the interactions of the submodels as the model steps forward in time. So the suitability of each submodel on its own doesn't necessarily tell you that the model as a whole is going to be suitable. So those are the reasons why they have this skeptical view. And there is some scientific acknowledgement of this holistic challenge, or like a version of it. So for example, like when we update a model, or when you, the experts, update a model, it's hard to know whether the improvement in model performance is a consequence of like a new improvement to a piece of the model's physics, or if it's a case of like compensating biases, or maybe it's due to how tuning was done in that new case. And so that would be a case, right? Tweaking a parameter, a single parameter for the sake of the whole model. So again, this idea of holism is at issue there. And another concern that scientists have is that we don't have enough good observational data to evaluate current models to the extent that we would like to evaluate them. Of course, we don't have observational data of future climate, for example. And these are all concerns that scientists have raised in relation to the holistic challenge. So in the scientific literature, folks who have cited Leonard and Winsberg then have gone on to talk about these types of challenges. And I think these are all like legitimate concerns, and they're sort of like variations on the holistic claim. But the original philosopher's claim of holism is much broader and I think more extreme than what is indicated by the concerns here, and it's more extreme than what is often recognized. So maybe a way to pursue this a little bit further is to separate the holistic challenge. So maybe based on scientists' specific concerns that I talked about on the previous slide, we'll get one definition, and then the philosopher's blanket statement will give us another definition. So the tame version states that it's difficult to evaluate model successes and failures in a piecemeal fashion, whereas the radical version of this holistic claim states that it's impossible to do so, that we cannot, or experts cannot, evaluate model failures and successes in a piecemeal fashion. Now, obviously, most scientists would endorse only the tame version, and some philosophers and scientists have debunked the radical version by focusing on things like how model successes are attributed in the literature. So this is like the whole literature on robustness and why the good features of the climate model are responsible for them getting the right results for the right reasons. But I'm not really going to go into that today. Instead, in this talk, I'm focusing on model failures. So specifically by model failure, I mean model error or model-model discrepancies, as well as any discrepancies between model results and other data. So any disagreement between these sources. And of course, scientists can and do evaluate model error in a piecemeal fashion. So we can think about this in the case of single models, and the first example I have will look very familiar to all of you. You probably know much more about this example than I do. Has to do with CESM2 in a recent diagnosis case. So this comes from the Wall Street Journal's write-up, which I think that the title that they have here is a little bit misleading for what I want to say about it, but this was sort of a high-profile example that was written up and has a pretty broad audience. So the short story is that CESM2 is running too hot. It's much more sensitive to forcings than expected. And then the Wall Street Journal says a bunch of things, but one of the things they do focus on is how scientists figured out, like unraveled this mystery of why the model was running too hot, or started to unravel the mystery. So quoting from the Wall Street Journal, it says, in their initial analysis, scientists discovered a flaw in how CESM2 modeled the way moisture interacts with soot, dust, or sea spray particles that allow water vapor to condense into cloud droplets. It took a team of 10 climate experts almost 5 months to track it down to a flaw in their data and correct it, the scientists said. Through field experiments, they next learned that bright low-level clouds off Antarctica's coast were neither ice crystals nor cloud droplets, as models assumed, but rather a supercooled liquid that affected how clouds cooled the surface. Since releasing the open source software in 2018, the NCAR scientists have updated the CESM2 model 5 times, with more improvements in development. We are still digging, says Jean-Francois Lamarck, director of NCAR's Climate and Global Dynamics Laboratory, you guys, who was the project's former chief scientist. And another quote, it's going to take quite a few years. So that, again, was all directly featured in the Wall Street Journal article. And I know this isn't the whole story. For example, there's a process-based analysis in the scientific literature that looks at, that isolates different specific cloud feedbacks and their strengths and runs CESM2 a bunch of times to do that. But at the very least, it should be clear that scientists can identify the reasons why a particular model gives results that are at odds with expectations. The radical holist claim that this cannot be done appears to be flatly false. Another case, much further back in time. So that one was from a couple of years ago. This one's from decades ago. This table is from an old study in 1983 from Hansen et al. The header that says test run, physics change, and major effect suggests the methods that scientists use in this study also involves a sort of error diagnosis or model behavior diagnosis. So before AMIP, or before the organized coordinated model intercomparison projects, there are still cases where models were compared in a broader sense. So this, I like to think of this as like an intergenerational model comparison, a comparison of one model to itself over time as it's developed. And so here we can see the scientists make one physics change at a time and observe the effect. And this sort of strategy of change one piece of physics and see what happens allows us to isolate the impact of physical processes on the whole model's output. So again, it seems like the radical holist claim is flatly false, at least in the case of a single model. But what about error diagnosis in the multi-model context? This is something that I started to become more interested in because thinking back to that claim from Leonard and Winsberg, the philosophical skeptical claim, all of the evidence that they focused on was from the multi-model context, how it was difficult to track down relative model errors that were being intercompared with one another at a large scale, like dozens of models all being evaluated together. So I think the holist challenge is deeply relevant to the multi-model context, especially since MIPS help inform us about future climate change, and model spread, or like the disagreement between models, is often analyzed in terms of its implications for uncertainty about future climate. So even if the holist challenge is false in the single model case, it's worth thinking about in the multi-model case, lest we find ourselves in a situation where individual model errors can be tracked down, but the reasons why different models give different answers remains out of reach. I don't think we're in such a situation, but I want to think more about why that is. So I suggest that examining error diagnosis in multi-model studies will be both philosophically and scientifically informative. So philosophically, studying error diagnosis can reveal an underappreciated sense in which scientists understand their models. And scientifically, studying error diagnosis can provide us with what I hope are the ingredients for an error repertoire, which hopefully can guide future error diagnoses. And there are three questions I think worth addressing here, at least as sort of a starting point. First is, why is error diagnosis difficult in the multi-model context? How are model errors nonetheless diagnosed? Because they are. And then how can error diagnosis be improved? So to address the first question of why it's difficult to identify errors in a multi-model context, we might think about how errors are identified and explained for a single model. So I think a useful way of thinking about this is provided here by Stephen, in a quote from Stephen Schneider in his talk from a very early model intercomparison project back in 1978. So Schneider says, he refers to something he sort of informally calls the first law of climate modeling. That is, to use climate models to understand cause and effect linkages in the climatic system, it is necessary to make no more than one change at a time in a model, be it a boundary condition, numerical scheme, or physical parameterization. But obviously, this isn't a viable strategy in the multi-model context. Why not? Well, first, models differ from one another in a multitude of ways, and these differences aren't like prescribed or systematic across different modeling institutions. In multi-model studies, the relationships across the models diverge sort of significantly or markedly from the prescription of Schneider's first law, that one change at a time law. So a clear example of how models differ in this way, going back to the IPCC's fourth assessment report in chapter 9, there's this nice description of how different climate models represented aerosols differently. But the models didn't just differ with respect to aerosol representations. So instead of a hierarchy in which they only differed with respect to that one feature, they also differed with respect to like other aspects of model structure and their resolution, and other features as well. And so there's a multiplicity of intermodel differences. And then the second issue, I think, has to do with the dispersal of expert knowledge about climate models. So the knowledge of model components and their associated strengths and weaknesses are sort of it seems to me anyway, they're dispersed across different institutions and across different groups and individuals within those institutions. So today with the most complex models, I mean, correct me if I'm wrong here, but from talking to some scientists, it seems that no individual scientist fully, knows all the ins and outs of an Earth system model. The total knowledge about a given Earth system model is collective, and the total knowledge about all existing Earth system models is like collective squared. I mean, it's really, really dispersed. And of course, as the number of models continues to grow, I think there are like over 100 models participating in CMIP 6. This problem may appear to become more and more intractable. And yet, so that's the problem side of things, and yet multi-model errors are diagnosed in practice, and they have been for a long time. So scientists often explain why models are disagreeing with one another and why those models are disagreeing with observational data. They've been offering these explanations since the 70s, but especially in the 1990s following the first iteration of AMIP, the Atmospheric Model Intercomparison Project. There's a rich variety of studies which diagnose model error. And today, process-based analyses are becoming more common and more commonly advocated for. And these are studies which examine like the representation of specific weather and climate processes rather than just like a single variable. And they use representations of processes to identify model adequacy and model error. And from what I've seen, these can be done in a variety of ways, at least as I've seen them in the scientific literature. But I propose that perhaps we can benefit from a systematization of these practices that are already being done. Okay. So now on to some examples of model error diagnosis in the model context. The sample of examples that I look at is sort of biased according to my own interests, but at the same time, I think that they capture some different features of error diagnosis that I hope you will find enlightening, perhaps very familiar. Okay, so the first example comes from a study in the 90s. This is one of those analyses following AMIP. And it's a study from Gleckler et al. The short story is that the scientists attributed incorrect calculations of ocean heat transport to the model's representation of cloud radiative effects. So each line in the figure is a different model. Heat transport along the meridian is expected to be northward in the North Pole and southward in the South Pole, or sorry, northward in the Northern Hemisphere and southward in the Southern Hemisphere. But we don't really see that here. The models are showing heat transport in the wrong direction in the Southern Hemisphere. And so the scientists infer that cloud radiative effects are the culprit. And what they do is they identify this and then they recalculate ocean heat transport using sort of a hybrid of model data and observational data, like a hybrid version of cloud radiative effects. And when they do this, when they recalculate it using the hybrid version, voila, they fix the error. And so this sort of supports their diagnosis. The second example is another one from the 90s. It comes from Sengupta and Boyle. And rather than offering like a physics-based argument, they instead use a dimension reduction technique, principal component analysis. And so the idea here is to group models in terms of statistical similarities between their components. So the left two models have components that look similar in terms of their variances, and so do the right two models. Now the authors thought initially that models, the first, third, and fourth model here would all be grouped together because they all use the same convective parameterization. And I thought that that would be the determining feature. But what it turned out, how it turned out is they found that the representation of vegetation and some other features were more important, which is why we have the groupings models 1 and 2 together and models 3 and 4 seen here. So this technique of principal component analysis could be used to highlight the relative importance of different parameterizations when assessing model behavior, which perhaps could be a precursor to a more involved process-based analysis. An explanation of not just why they're grouped this way, or not just that they're grouped this way, but why they're grouped this way. Okay, so my first two examples were early ones from the 1990s. The next two examples are more contemporary. So this one is a study, it's an analysis of regional climate models with the authors Bukowski et al. From 5 or 6 years ago. And they determined that a particular GCM used to drive the regional models led to a poor representation of the upper level jet stream. So this can be seen by comparing the middle series of panels, which are the model simulations, with the top panel, which come from observations. And so the analysis in their study is dynamic. The upper level jet stream simulated by the model is, I'm quoting them, too weak, positioned incorrectly, and it does not evolve properly through the summer, end quote. So the poor simulation of this process as it evolved over time tells us why we should expect a poor simulation of that same process. The poor simulation of this process in the present day case tells us why we should expect a poor simulation of that same process using the same combination of models in the climate change case, in a future scenario. So error diagnosis here amounted to determining whether processes were being simulated accurately, and if not, why not? In this case, the global model providing the boundary conditions for the regional model was the culprit. Okay, and then my fourth example, this is another contemporary one. Again, this isn't meant to be like a systematic sampling of all model intercomparison literature. So this one comes from GeoMIP, which I think is a great example of a very precise error diagnosis. So GeoMIP is the geoengineering modeling intercomparison project. And so these model experiments typically involve like reducing the solar constant or simulating injections of aerosols into the stratosphere to deflect sunlight. Anyway, what I find interesting in this study is that only 4 models are evaluated, and this allows the scientists to go into some details about each of the models that would normally not be feasible if they were looking at, say, dozens of models at the same time. And for each model, many of the features of each are detailed early in the paper. Some summary of those 4 models is given here. And the scientists also explain the previous diagnostic studies that each model has been subjected to, which I think sort of highlights the importance of background knowledge and error diagnosis. And then when they evaluate the model results, they focus on offering a detailed physical explanation and tie this to specific features of the models. For example, they highlight the fact that one of the models does not include heterogeneous chemical reactions on the surface of aerosols, unlike the other models. So that's what I've boxed out here in the green box in the yellow circle. And this singular difference about the representation of heterogeneous chemistry on aerosols is linked to differences in ozone loss at different altitudes in one of the models compared to the other models. And according to the authors, and I have a sort of a long quote here, so bear with me, the missing heterogeneous chemical reduction of nitrous oxides on the aerosol surface area density does not allow in this model a limitation of ozone loss above 50 hectopascals. This ozone reduction consequently reduces adiabatic heating, resulting in polar temperature decreases larger than that in the other models, at least for certain altitudes. And then they go on and offer some more details. And I'll be honest, I don't have the expertise to judge whether this diagnosis is correct, and I don't follow the specific exact details of the explanation, but it seems that the scientists are pointing to singular model differences and offering a physical explanation of why that model difference is relevant to that model's anomalous behavior. This is therefore another clear example of error diagnosis in the multi-model context. Okay. So from these examples, I think we can sort of list some general strategies of error diagnosis. So this is kind of a summary of what we've already seen. So on the one hand, scientists often reason about known physical relationships, and sometimes they test their diagnoses. And we saw this in the first example, the one with the ocean heat transport and the hybrid model observation calculations of heat transport. Then there's the idea of evaluating model output dynamically and focusing on processes as they evolve over time and whether or not those representations are realistic. And so we saw this in the regional climate modeling example. And then this fourth bullet point, this idea of making use of expert knowledge concerning previous model or parameterization behavior. I think there's a lot more to be unpacked here. It's not something that I can go into much on my own because I don't have the expert knowledge, but I would love to chat with you all about that. I think this idea is fairly broad though. In several of the studies, it was explicitly stated that like a particular parameterization was associated with a particular bias. So like this previously known biases of specific model parts were thought to be relevant to the error diagnosis. And like also in the GeoMIP case, a full suite of model diagnostics was given in the early part of the paper. So I suspect that expert background knowledge about each of the models figured into the very detailed error diagnosis that they gave, even if they didn't make all of this expert knowledge explicit in their analysis. Another strategy, as I mentioned, using dimension reduction analysis to identify explained variance. So we saw this in the Samgupta and Boyle example. And then finally, this isn't really a strategy by itself, but it is an interesting component, I think, which is to evaluate a smaller number of models rather than a larger number, just because it may be more practical or feasible to highlight relevant model differences when you're dealing with a smaller number of models. Okay, so based on the examples I've considered and the generalizations that might be made from them, I think we're now in a position to talk about an error repertoire. So this is a proposal that I hope generates some scientific interest, as I certainly have a philosophical interest in it and in the value of errors and disagreement more broadly. So the way I'm thinking of it, an error repertoire would be like a systematized catalog of already diagnosed errors, as well as a set of recommendations for how to evaluate model errors in future applications. So some very broad ideas are listed here. Similar kind of to what I just said, there's the idea of building and consulting a list of errors that are expected or commonly encountered. So this would be really just systematizing or formalizing what's already done. For example, in the Gleckler et al. Study, the one with the ocean heat transport, the authors state explicitly in the paper that, quote, GCMs are known to disagree considerably in their simulations of the effects of clouds on Earth's radiation budget. And then they cite a previous study which establishes this. And then they go on to say, and hence the effects of simulated cloud radiation interactions on the implied meridional energy heat transports are immediately suspect. Or in another case, in the regional climate modeling example, there's a section kind of separate from what I talked about, where they talk about previously known behaviors of different convective parameterizations and how they may be relevant to what they're seeing in their in the simulations that they're looking at. So there's a lot of common previously encountered biases that are informing future diagnoses. The second piece is sort of overlaps with the first one, but I think it's important to highlight it anyway. It's the idea of recognizing errors based on their plausible effects and then looking for instances of those effects. So this involves relating expectations to their downstream consequences. So it may be determined that a convective parameterization, which convex too easily, will likely lead to a certain type of precipitation bias. And this is something that's talked about in the regional climate modeling study. In the same sort of way, it may be determined that a model which doesn't represent heterogeneous chemistry on the sulfate aerosol, thinking back to the GeoMIP example, will cause a specific bias in ozone loss at a certain altitude. So the main idea with 1 and 2 here is that if we have them and enough information is documented, then maybe error diagnosis can proceed more easily. So if these things are sort of made more publicly accessible or accessible to different subcommunities in climate science. But there's also more to this proposal. So ideally, model error diagnosis could be done in a somewhat less post hoc fashion. So this would mean predicting certain model disagreements or making explicit what types of model errors are expected. And these like quote unquote predictions, they could be tentative or suggestive and coarse grained. but they could lead to model error diagnosis being more commonly practiced, which could in turn lead to improved understanding of the climate system and more efficient development models. Okay, so overall, I think that an error repertoire could have multiple benefits. First, I think that pinpointing model biases relative to other models and explaining those biases in terms of model components could help when prioritizing areas of focus in future model development. Sort of streamlining error diagnosis to make future diagnoses easier and more informative for those who maybe learn from them. Second, I think that the practice of identifying model errors in a systematized and maybe more widely advertised way could demonstrate a deeper understanding of complex model behavior. This is especially the case if model errors can be predicted to some extent. And so an error repertoire might also be helpful for other climate scientists who want to use models, but maybe they themselves weren't involved in the development of those models, or they don't know about the model's past errors or behaviors. And finally, I think there's another sort of advantage to demonstrating a deeper understanding of model behavior. And this comes going back to my interests as a philosopher of science. So philosophers of science who are looking for a response to this holistic challenge, I think having an error repertoire would provide a much stronger basis for saying, hey, scientists can and do diagnose errors. Here's why. I think having that in a more systematic presentation of that could be much more convincing and educational than the hodgepodge of examples that I went through today to show that errors are diagnosed. Okay, now I recognize that there are some hurdles facing my proposal. This project seems like it will be a huge undertaking, and it may be unclear what the first steps should be. Should individual model errors be prioritized, or should model biases relative to other models also be documented? So where to start and how to motivate other people that this is the type of thing worth doing. And second, admittedly, my list is incomplete and currently coarse-grained. A fair question, I think, at this point is, are the types of diagnoses that I've outlined helpful for categorization? Perhaps some of the examples I've considered would not be accepted by scientists as genuine examples. Maybe we only want to count the process-based ones, for example. Or perhaps there's a diagnostic strategy that I've just entirely overlooked. So another limitation is that my study is, based entirely on, almost entirely on reading and finding what I can in the scientific literature. But what about what's going on behind the scenes? And so this is where I would love to hear from you all. You have insider knowledge of how climate models' different parts are built and tested. You have insider knowledge of what might be prioritized when anomalous results are encountered. So are there error diagnostic strategies to add to my list? Is there a level of depth to this type of work that just can't be found from looking at the scientific literature, or maybe just the scientific literature that I've looked at? And then there's this third issue of, is this project worth pursuing further? Again, I would love to hear from anyone who has insight about this. Comparing perspectives about modeling institutions could also be a fruitful direction to take this. Insider knowledge at one place, say at NCAR, versus insider knowledge at another place. Maybe there are some interesting differences between how this type of thing is done behind the scenes, not in the scientific literature. Okay, so I want to move on to the second main point that I wanted to argue for, although I'm not going to spend nearly as much time on it as I just did with the error diagnosis stuff. I hopefully the idea of an error repertoire intrigued you, or maybe you have a knockdown argument against why it's a foolish thing to be thinking about. Either way, I would love to hear it. But now I want to touch just a little bit on this idea of the value of low skill models. And this is something that I write a little bit about in my dissertation, but I think there's more work to be done here than what I'm going to present. These are just a couple of case studies that I think are thought-provoking ways of thinking about low skill models and how they might be thought of as valuable for science. So the question at hand, are there other non-intuitive scientific benefits of climate model intercomparisons? So we saw that error diagnosis in multi-model studies can have scientific payoff, can lead to enhanced understanding of model behavior. And I see this as a sort of underappreciated value of model intercomparisons. Typically the attention, at least for philosophers of science writing about climate models, the attention is on things like robustness and the significance of model convergence, or different statistical interpretations of model independence. But the topic of error diagnosis shows that there's another area worth exploring, and I think yet another underappreciated topic is the value of low-skill models. I know the idea of model skill has been debated somewhat, so I'm just going to offer like a sort of a quick and dirty definition of a low-skill model just for the purposes of demonstration. So we can say that a low-skill model is a model whose results fit some observational data for some variable or variables of choice less well than other models fit that same observational data. So a model that fits some observational data less well than other models do. Okay, so to demonstrate this, I have sort of two case studies I want to talk about. So the first is an example of an emergent constraints approach, which aims at narrowing the estimate of a particular climate variable. And so in this case, the scientists analyze how model simulations of recent historical temperature trends correlate with model simulations of transient climate sensitivity, TCR, which is a measure of climate sensitivity that describes how global temperatures increase when CO2 concentrations reach a doubling after gradually increasing over some time period. And so this example comes from Jakorska et al. In 2020, just a few years ago. And ideally, in these types of approaches, scientists want to be able to say that because the model output of recent warming correlates with model estimates of TCR, and because we have observations of recent warming, and because there's a well understood physical relationship between recent warming as CO2 concentrations increase, and a relationship between all of that and TCR, then we can use this correlation to narrow the estimate of TCR. And so without going into the details of this example, I want to point out that because this sort of relies on a correlation, even the models which are too hot, that is the models in this orange box in the upper right-hand corner, they seem to be valuable for this analysis in some sense, at least in the sense that they help us scientists establish that there is indeed a correlation between recent warming and TCR. These models are too hot compared to recently observed warming, but they're consistently too hot. They have low skill relative to the other models for this variable of recent temperature trends, and yet they play a helpful role in this analysis. And I think there's more to this example than I've just explained, but this is sort of the gist, the stepping off point that I've been trying to think more carefully about. Okay, so that's one example. And then the other example, sorry for the big block of text, but I didn't have a good figure to go with this one. Another example where low skill models I think are scientifically valuable is in perfect model studies or model as truth studies. So these are sometimes used to provide auto-sample tests for model weighting schemes. So the key idea is written on the slide, although I've omitted some of this as a sort of a simplified version of it, but I think it's helpful to just read through the whole chunk of text here. So the basic idea is, say you have an ensemble of 30 models, each of which has simulated 20th and 21st century global precipitation patterns. The model as truth method involves arbitrarily removing one of the models, which we'll call the true model, from the ensemble and then treating it as if it were the observational data. Then the remaining 29 models are weighted based on how well they fit the true model for the 20th century time period. Next, the weighted ensemble is evaluated against the true model for the 21st century. A comparison is then made to see if the weighted ensemble does better than the unweighted ensemble. And then this is repeated 29 more times with each model in the ensemble taking the turn as the true model. So the idea is to use models to generate like pseudo observations. We just pretend that their output is truth and see if the model weighting scheme, the equations that we decide to use to weight models, if we do weight them, see if it works in a future case based on how it was implemented in a past case. And so as with the emergent constraints example, even the low skill models that maybe eventually be downweighted to like 0% in the ensemble, they're still used in this type of analysis. So to repeat, even the models that may eventually be downweighted, say based on their relatively poor fit with observations compared to the other models, they still play a role in these perfect model studies. And that's to help test the weighting scheme for the remainder of the ensemble. So the low skill models are still useful for improving projections of future climate. They help provide an additional test for model weighting schemes to pass. Of course, this is only true insofar as scientists trust these low skill models to represent climate accurately enough to serve this role. So like if a given model simulates climate in a highly unphysical way or a highly anomalous way, then maybe they wouldn't bother using them to play the role of truth. So it's not that any low skill model adds scientific value. It seems to be more that low skill models which surpass a certain threshold, maybe in terms of skill, but also in terms of like how physically meaningful they are or how physically meaningful their behavior is. These types of low skill models can add scientific value, even if they aren't directly used in projecting future climate. They can help come up with a weighting scheme that can be used on an ensemble that is used to project future climate. Okay, so those two examples are just some things I've been thinking about in relation to the value of low skill models. I don't have a concrete scientific proposal for for those two examples or that idea, but I hope that you find it intriguing. And with that, I will say thank you for your time, and I look forward to any comments or questions or critiques. So thank you very much.
Great. Thank you, Ryan. So I'm going to open it up to questions. So there's 3 ways we can do this. So if you are on the Zoom call, you are welcome to raise your hand, ask your question orally, or if you want to put a question in the chat, that'll work as well. And if you happen to be streaming on YouTube, you can go to Slido and insert a question into our Slido page. And the way that you get to that is slido.com. And then you input hashtag CGD seminar. So I will see if people want to raise their hands, put something in the chat. All right. So Dan, go ahead.
Yeah, thanks a lot for a really interesting talk. I guess throughout there were just, what you were discussing was ringing some bells for some of the things that we do in data simulation and parameter estimation. I was wondering if you thought about it in that context. For instance, we're often, I think maybe what you would call an error repertoire, we think of as maybe the spread that we have among different models themselves or parameterizations of these models. And so in some contexts, we're very interested in maintaining a spread, but particularly one that we think reflects an underlying probabilistic distribution of what models should actually look like. And indeed, one of the ways that we test that is what you, I think, just talked about, which is kind of grabbing one ensemble from a larger ensemble and doing these kind of imperfect model things. So anyway, I was wondering if that could, as a framework you've also thought about.
Yeah, admittedly, I haven't thought as much about that as I probably should. And I would be interested in learning more. The first, I want to see if I'm clear on it. So you're talking about evaluating spread of, say, specific parameterizations and quantifying that. Does that, I guess, for the error repertoire idea that I was thinking of, does the story end there, or does the spread in parameterization output, is that linked to general model output at a later stage, or is it sort of just documented and for reference?
Yeah, there's a lot of different things you can do with it. So at first blush, I mean, I think what we do in data simulations is to compare the spread of the model to the uncertainty of your observations. And then what we'd like to do is to update the spread of, say, an unknown parameter as we proceed. And so it's about evolving this probability distribution function. But so it's an integral part. Thinking about that spread is really integral to what goes on.
Okay. Yeah, I mean, thinking about this in relation to data assimilation, this could be a fruitful way to take this. I mean, if I can just ask you one question. So based on the suggestion that I had, does it seem like it's sort of like my suggestion is kind of naive, and that actually what you guys are doing is a little bit more sophisticated, and it's already being done? Or do you think that there might be room for further steps to be taken?
Oh, I mean, I don't think it's naive. I think it's a powerful suggestion. It's among the things that people are currently doing. So I think it's a useful tool, and maybe underutilized for some of the climate questions you might be interested in.
Okay, cool. Thank you.
Okay, thank you, Dan. So any other questions? Again, raise your hand, put things in the chat. And I'm not seeing anything come in on Slido. So, all right, Peter Lawrence.
Hi, Ryan. I really liked your talk. That was great. This whole idea of having like a portfolio of like errors which we know within models or representations that cause certain behaviors, I think is really great. But sometimes, we're looking at emergent properties. And doing that causality back to this is the reason why a model does this it seems like it's nice and deterministic, but the reality is like getting that process level understanding is hard. How do you go about saying, well, okay, you might have something that say runoff is too high in this model, but then it changes soil moisture and properties and everything else, and trying to get back to a causal sort of like statement of this is why this model is different. How do you go about that? That's kind of my question.
Yeah, I mean, I wonder in the case of emergent properties, I guess maybe perhaps part of it comes down to how those are looked at as like insensitivity analyses. So how the emergent property of interest changes as the model is being messed with or improved throughout that whole process. But when it comes to like, you're focusing on one emergent property and how that is being affected by changes to the model, and then you forget, oh yeah, there's another emergent property that I'm interested in, and I wasn't even paying attention to that. I guess that the question then seems to me to be kind of a difficulty in prioritization. So you can explain anomalous model behavior or new novel model behavior for some uses, but then you forget that you want to use the model for something else, and maybe you weren't focusing on that through the development process. So I'm not sure. You raise a really great, very challenging question.
And I just thought it was interesting, like if you go back to the older models, you can do that sort of level of differences and being able to see sort of emergent properties and changes. But the models become so complex, and the interactions and the systems are really hard to actually do that direct causation, I guess. That was what I was trying to get at.
Okay. As a sort of question for you then, so I had that slide with the Hansen et al. Example from 1983. So you're saying that type of activity no longer feasible with our current models?
That's what my concern is. Like our models have got more and more complex as like we've sort of taken them and developed them as generation after generation. So now the complexity of the models is hardened to that level of process determination of the reason why this model is different to this model because of X. And I think it's really valuable. I think that having a place where you could go and look at a model and say, oh, why does this model not have the right amount of, I don't know, crop yield for a particular, investigation. So that model does that before you even start thinking about, well, how do experimental design now? As a fundamental part of experimental design, you want to know what the limitations of the model are. And so I like the idea of having a list of this model has these problems, but just determining what those problems are and why they're there seems sort of like a big challenge. That's all.
Right. So maybe the error repertoire, the listing of errors would be a lot easier. Would be much easier to accomplish than the list of the explanations of why the errors were coming up.
Absolutely, yeah.
Thank you.
Okay, thank you, Peter. And quickly, Ryan, the Hansen et al. From 83 is the claim that you should do one change to a model at a time. Is that right?
That's just what they happen to be doing because they have their model 1 and they build model 2 from it, and they document how they did it.
Yeah, okay. I would just add that I don't think, especially in the context of how CESM is developed, and then there's so much distribution of labor and individual component development that that you can't really do one thing at a time because so many people are working on it and making so many simultaneous changes. So it's a difficult thing to track. Seth.
Hi, Ryan. Thanks. That's a really nice talk. I enjoyed it.
Thank you.
One other value of low performance models, which it wasn't clear to me whether or not this was included in what you were talking about, is that there's a lot of analyses where it's really useful to have something, one of the things in your analysis that you're comparing to of something that is doing a bad job, because we're often fighting against, this cognitive bias of the name of it dropped out of my head, but checking only to see whether confirmation bias. We're often fighting confirmation bias. And so, if you don't have something that is doing a bad job in there and all the results look kind of similar, or they all look sort of like equally different from each other, it can be really hard to tell whether that means that everything is doing a good job, or whether, only one thing is doing a good job and there's a lot of really significant differences between things. So and sometimes you can, take one of your existing data sets and like scramble it or something to produce something that is a good comparison of this one I know is not doing a good job. But other times you might want something that sort of looks pretty realistic but has a known flaw in it. So that's another area where I think it can be really valuable to have a model that isn't good.
Thank you. Is there a name for that activity, or is this more of just a general practice?
I don't know. If you can come up with a name for it, it would be, I'd be interested in that also.
Okay.
That's great, Seth. Thank you. Peter has his hand up again. So go ahead, because we only have a couple minutes left.
Absolutely. One thing I did want to say is the CAM 6, CAM 5 changes, they did go back and take out every single major development one at a time to work out what they were individually doing. And that was something that Cecile Hannay was behind, doing that exhaustive testing of each of the components of the differences to try and work out why the model was so different, why the climate sensitivity changed, which actual part was it the microphysics of the clouds, was it different things in convection, that they went back and did all those steps. So there is the ability to do that. It just takes a lot of effort and a lot of time. And so if you wanted to talk to Cecile, and she'd be able to give you good insight to how they did that.
That could be really helpful. Thank you.
Yeah, and quickly, Rich might know, was there something published based on that research that Cecile did, the comparison between CAM 5 and CAM 6?
Not to my knowledge yet, no. I mean, I know that a lot of people I'm looking at it. I know other groups are looking at it as well. And it's a great data set, incredibly difficult to understand and it attributes certain things in a linear sense. So good luck.
Okay, thanks, Rich. All right, Frank, I'll let you have the last question. Go for it.
Okay, thanks. More of a comment, maybe asking you to react to it, and that is, sort of an alternative perspective is that we should fix the things. Well, your suggestion seemed to be that this error repertoire sort of and MIPS identifying the most serious bias as a basis for prioritizing model development. An alternative, somewhat of an alternative, is the perspective that's sort of taken by some of the climate process teams, that we should prioritize the processes that we have the most confidence that we know how they should be represented in the model, that we should fix the things we know best and take those off the table. So it's sort of a process of elimination. They may not be associated with the largest bias, but it increases our confidence that the process collection of process representations in the model is more accurate progressively. So that I'd be interested in your reaction to that.
Well, that seems really like reasonable to me. I guess I can imagine perhaps cases where those two things are in tension, where you know that a particular process representation is just so problematic that it's causing enough biases where you would want to prioritize it over the other ones that you know how to fix better. And then it becomes a question of, we know we need to make all of these fixes. How do we order them? And I don't know if there's going to be like a principled way for people to say that you definitely have to do this one first and then this one. I think that there could be a lot of reasonable disagreement about that, but that it would be helpful anyway to still have the error repertoire in that case.
Thank you.
Okay, thank you. So if we don't have any remaining questions, I'd just like to thank Ryan for joining us today. And we will be back to in person next week. So I will see you all in the main seminar room. Thank you, Ryan.
Thanks for having me. I really appreciate it.
Okay, thank you, everybody.
All right. I will see you later, Monica. I might.
Yeah, thank you so much.
Yep,
I
thank you.
will see you later.
All right. Bye.
Bye.